Assalamu alaikum. So today we will be starting a new chapter, which is organic chemistry. Uh, Not actually we are going to start it. We will be like having a sort of in-depth overview and in-depth analysis of the organic chemistry for the syllabus of like A2 level. Because there is like two portion for A levels. There's the portion of AS level and there is the portion for the A2 level. So A2 level, like we will be considering benzene most of the time because benzene is a like sort of a massive topic. So that's why Cambridge has decided to follow the portion of that like the other part in the AS, while the benzene part in A2. So we will do the AS part later on, but today we'll be starting with the part of A2. So it is benzene. So in between, I will be like describing and if the terms and the words, if they are like from the previous uh, the first half of the syllabus, which is the AS syllabus. So I'll be like describing in short and brief. I will be giving brief description in order to have a consistent flow. So now we have some characteristic reactions in the organic compounds. So there are like organic compounds, for example, alkane, alkene. Then we have halogenalkane. Then we have carbonyl compounds. And we have benzene. Benzene is also known as arene. Now, what were alkanes? Alkanes were like the hydrocarbons where the general formula was like CnH2n, CnH2n plus 2, sorry, CnH2n plus 2. So the structures were like if we gave if you try to give an example, so one of the like example could be this one, which is methane, CH4. Another could be C2H4, C2H6, or which is C. We have a carbon bond and six hydrogens. So this is a C2H6. Then for alkene, the general formula was CnH2n, and the formulas like the smallest molecule could be uh, double bonded C2H4. Remember, in alkene we must have a double bond, so there must be the presence of the the double bond here, which is the alkene bond, or alkene group, which shows this is the alkene group. CH C2H6. So since in a single carbon there are no double bond could have been occurred. So the single carbon element of alkene doesn't exist. That's why this starts as like ethene. It starts at ethene. Now for halogen alkene. Halogen alkene is simply like the same formula, or you'll get the same structure as like the alkene. Just any of the hydrogen will be replaced by an alkene and like a halogen group. So halogen groups are what? The group 7 elements are known as the halogen groups. Group 7 elements are what? Fluorine, chlorine, bromine, chlorine, bromine, iodine, astatine. Now, in our normal atmosphere, they exist as a diatomic molecule because they cannot like exist as free radicals. Single atom, they cannot exist because they're very like reactive, so they tend to have this diatomic molecules. But while they're forming halogen alkene or any sort of other compounds, they tend to break the bonds, like the bonds, diatomic bonds between them. They break this bond from the reaction and forms the compound. Halogen alkanes, let's say the smallest one could be halogen 2 uh, this we name this like there are certain naming conventions, but we can name this halogen alkanes in two ways. One is uh, methyl chloride. So here we have a methyl group. So if any of the alkene group does not have or we can say just have three hydrogen, one carbon, we can consider it a methyl group. So this is or alkyl group. This is an alkyl group. Since there is like one hydrogen, one hydrogen is less here, so that is considered as methyl, and there is this chlorine, so this is known as methyl chloride. Or we can say the name is also known as um, fluoromethane. Yeah. So one of the naming convention is methyl chloride, like giving the name of the alkyl group first, then the halogen, or we can say it is fluoromethane. So if instead of chlorine there was bromine, then we have to say bromomethane, or fluorine, then fluoromethane, then iodomethane, and the other one I don't know. So let's not talk about that. Now we have the last one, which is the benzene. Now, the benzene is the the benzene is the component or compound which we'll be studying. So I'm not giving the structure right now because we'll be having a detailed session from now on based on benzene. And the others are the component, like the other four are the component which we have studied so far. Oh, one more thing I forgot, which is carbonyl compounds. These carbonyl compounds are of two types. One is ketone, mm, another is aldehyde. So one is ketone and another is aldehyde. So there is a presence of C double O bond. For aldehydes, just a minute, let me be sure if I'm correct or not, like the structures, because so aldehydes are those which has this CHO group. So this is known as a CHO group. CHO group. Whenever you see there's a CH3, CHO has been written, do always remember this is a aldehyde group. It's better whenever they write a formula for you, the molecular formula, structural formula, you should draw the discrete formula so that like it becomes easy for you actually what but the most oftentimes with it, like it's not like understandable by just observing the molecular or structural formula. So you must, I must say, you must draw the discrete formula so that you get which bond is like included and which bonds are not included. Trust me, it makes it a lot clearer. Now, aldehyde has this CHO group, and anything could be here. It could be CH3, it could be another H, it could be CH2, it could be no sorry CH2, it could be Ce2H5, anything it could be here. So this is R means there is the presence of an alkyl group. Also, this alkyl group could be a hydrogen, but for ketone, it is only a COO group. COO group. Both the side there are. Remember, in aldehyde's case, this R could be H as well. This R could be H as well. So it could be, let's say, CnH2n plus 1. Okay. So here n could start from 0, 0 and onwards. But over here, this is also the formula for CnH2n H2n plus 1. But the only thing is the n should start from 1. Why? Because if n is 0, that means there should be a hydrogen. There will be a hydrogen. If n is 0, let's say C is 0, then 2 into 0 is 0 plus 1, so 1 hydrogen. So if R is represented by a hydrogen, see this becomes the same as this aldehyde. That cannot happen because the reactivity and the characteristic changes. That's why for ketone, it's going to start from 1, and aldehyde is going to start from 0. So these are the like the structures and formulas. Now, for their characteristic reaction, which I was like talking about, they have certain characteristic reaction. So for alkane, the characteristic reaction is free radical substitution, which is also a topic for the AS contest. So free radical substitution. Then we have alkene, which is electrophilic addition. Then we have halogenalkene, which is nucleophilic substitution. Nucleophilic substitution. Then we have nucleophilic addition. Finally, we'll be studying about benzene, which will be having electrophilic addition, electrophilic substitution, sorry, electrophilic substitution. Now, what defines how the reaction happens? For alkane, it's free radical substitution. That means, like, while telling about halogens, I just say, I said they're like they cannot exist as radical, isn't it? So, what does this radical mean? Radical means if the components, the compounds must have, like, if they have, let's say, this bond between them, if this bond is broken, then what happens? This bond is actually a result of what? Sharing, like this bond is the result for the sharing of electrons. So chlorine and chlorine, they share electron, one from each side, and they form this covalent bond. So when the bond breaks, each of the electron is, like, they get back each of their electrons, isn't it? That means there is an electron which is unpaired. That acts as a radical. This is known as a radical. The state of single atom, or the state of having an unpaired electron. An electron which does not have any pair, which is alone by itself. That's known as the radical. Now this radical can, let's say, if this is our this is our alkane, let's say if this is our alkane, and free radical substitution happens how? This bond of carbon and hydrogen, here also, like, sort of this reaction happens. They break the bond. After breaking the bond, they form this radical, and this hydrogen also form the radical. This chlorine, there are two chlorines. One of the chlorine now comes here and forms the bond. So it is actually substituting this, like, hydrogen carbon bond with carbon chlorine bond, and this hydrogen is left with HCl. So this radical, or free radical, like the radical which has been freed, this free radical substitutes hydrogen from the alkane. So that's known as a free radical substitution. Now, see here, nothing was added, isn't it? A atom was substituted. Nothing was added. This atom, like, it was replaced by another atom. Now let's come to, like, alkene. What happens in alkene? In alkene, there is the presence of this double bond. Sorry, I just keep on giving more bonds. So this double bond, due to the presence of double bond, let's say a hydrogen has been given, or a hydrogen has been provided to there, like the hydrogen molecule has been provided near to this alkene. Now this hydrogen will also undergo some sort of reaction to break the bond. So this hydrogen, since this is a diatomic molecule, this is also going to break the bond, but this is going to influence this pi bond also to break. When the pi bond is broken, one of the hydrogen will form bond with one of the carbon, and another hydrogen will form bond with another of the, like, other carbon. So after the bond has been formed, what will happen? Already, like, one of the pi bond is broken. So one of the bond is broken. Now this hydrogen is here, this hydrogen is here. Now see one thing: is anything, like, eliminated? If any, like, is there anything which has been, like, gotten rid of? In, like, previously in free radical substitution, we got rid of the hydrogen. Hydrogen was totally removed, but here nothing was removed. No, like, I mean no atom is removed here, isn't it? Rather, this hydrogen, extra hydrogens are added to the compound. That means addition has been happening. So this is known as a, like, addition reaction. To be more specific, electrophilic addition. Why electrophilic addition? The first compound, like, the reaction happens in this way. This lone pair of electron, both the electron in this pair, this bond, both the electrons are taken by this hydrogen, one of the hydrogen. Then other hydrogen becomes what? Positively charged. So if this is positively charged, that like goes and reacts with this carbon. So this is like what? This H plus is actually an electrophile. Electrophile means which has like the tendency to lose electron, or sorry, which has a tendency to gain electron. My bad. So electrophiles are those which has a tendency to gain electron. That means it could be positively charged, or it can also be neutral elements, but that has to be the tendency, that has to have the tendency to gain electrons. So H plus in this case has the tendency to gain electrons to become neutral. So it goes and become like adds with the compound, with the alkene. So this is known as electrophilic addition. Now let's come to halogen alkene. Halogen alkene, as you can now see, as you can like see the name, so you can actually sort of understand what sort of reaction will be happening here. Substitution. So if there is just the alkane and there's the chlorine, let's say, mm, so let's say we are being like we provided with, let's say, uh, Br2, or let's say any sort of molecules. So from there, let's say this chlorine is going to replace, just a minute. So in case of nucleophilic substitution, so this is the halogen alkene. Now let's say we have sodium hydroxide here. So what is going to happen is one of the other part, just a minute. So over here, this sodium hydroxide has what? A positive and a negative charge on it. Now from this chlorine, like this chlorine, let's say, it is going to like have a hydrolytic bond fission. Similarly, one of the hydrogen from carbon, like from the other carbon, let's say, that is going to have a hydrolytic bond fusion. So this hydrogen and this chlorine, they are having hydrolytic bond fusion. Now what happens is, after this is being formed, this hydrogen and this chlorine, they get separated, they get like, eliminated from there. This hydrogen, when it is eliminated, forms bond with this hydroxide, forming H2O. Okay, and this chlorine, it forms bond with the sodium, forming NaCl. Hence, we're left with what? We're left with this one. So this is what is happening here. We're substituting, but at the same time, we're also eliminating components. So elimination reaction is also happening. This is one of the substitution reaction you can say. Another could be, let's say, another which is much more specific for this reaction could be when we add, let's say, um, when we are adding over here, let's say, so far I'm not remembering, like I can recall other reaction, but let's consider with this one. Let's move on to the next one because we need to cover a lot of other topics. So whenever I will remember, I will be like giving the examples. So let's now come for the carbonyl compounds. For carbonyl compounds, uh, for halogen alkane we just saw, isn't it? Like it was like what substitution happened, like the the, the place of, let's say, hydrogen and chlorine, like they were like removed, displaced, so substituted. Nucleophilic addition, in place of like nucleophilic addition, we are getting the carbonyl compounds. So let's say consider this halide first. Sorry, not halide, aldehyde. So you can see its addition. Obviously, that means some compounds, some like, atoms going to be added. So it's true, due to this double bond, let's say when it is further oxidized, this aldehyde is further oxidized, what it is going to do is this is going to break, and this is going to cause the formation of carboxylic acid. This is going to have like this, in some cases, these are the reactions which are going to take place. On the other hand, where we have, let's say, when we provide, let's say, cyanide, so we have this aldehyde and we're providing cyanide. So cyanide is provided in place of, like, in terms of the KCl, let's say potassium cyanide. So in dissolved situation, what is happening, this is the cyanide ion. Now this cyanide ion is going to simply attack this carbon. When it attacks this carbon, there is going to, like, be changed in, like, the one of the bond. This bond is going to be, like, moving, or this, like, electrons of this bond is going to get moved towards the oxygen, forming, like, making it partially positive and carbon partially, sorry, making oxygen partially negative and carbon partially positive charge. And when this reaction happens, there this intermediary state happens where it is O of uh, O, and oxygen has formed, like, gained the negative charge, so it becomes, let's say, the O minus. And there we have, let's say, these other parts, like like other atoms are have a, like, they're already there without, like, any hesitation, without any other alteration, so they're like normal in general terms. And carbon has sort of gained this cyanide. Carbon has gained this cyanide, and we have this hydrogen here. So this is the situation, like, so far now. Obviously, there is the presence of this negative charge, like the influence of negative charge, which causes this molecule to become negative. Now, how do we further verify, like, how this negative charge is going to get disappeared? There are obviously hydrogen cyanide, which is, like, acting as a catalyst, that is going to be provided there. So this hydrogen is going to come, or is going to get attacked by this oxygen. When this gets attacked, similar thing happens. This bond breaks. Finally, this is being formed as Cm hydrogen ROH. So this molecule is formed. Now see, a substance or a atom, or two atoms are actually, like, a group of atoms actually, like, get added with the carbonyl compound. One is the cyanide, another is hydrogen. So see, this is the, like, addition part. Like, they are, like, added. Nothing is being, like, eliminated. Now the second part is the nucleophilic part. So see, cyanide over here, it was what? A negative charged, like, ion. So a negative charge ion usually has what? A tendency to lose electron. It tends to, like, lose electron, to, like, donate electron. It can also be a neutral compound who has the tendency to donate electron, or who has the surplus of electron. If, let's say, the outermost shell electron has more than required electrons, in that moment it will be, like, having a tendency to lose electron. Those situations are very rare, but still, like, it can happen. So this is the nucleophilic addition. Now comes the final part, which is benzene, which we will be studying in greater details right now. And it is, as mentioned, it is the electrolytic substitution reaction. So let's study about the structure. So benzene has formula of C6H6. It has a formula of C6H6. Now, how it, like, looks, it looks like a hexagonal structure with a circle inside, like, as like the honeycomb. So we have seen, obviously, honeycombs. Honeycombs are having a shape of this. So that could be, like, sort of familiar, like a familiar sort of symbol. But let's define this shape a bit more into detail. So there are, like, six carbons actually in the six corners, which actually forms this hexagonal structure. So these six carbon obviously has, like, they are bonded with each other, but there's this question, then how are these, like, hydrogen defined? Is each of the carbon is having six hydrogen? Yes, actually they're having six hydrogen. So how is that happening? Because we so far got to know, like, each carbon has the maximum capacity of forming four hydrogen, like four bonds. So, like, they usually, like, they do generally tend to form this four bond. they, like in general, like they do not tend to form like less bonds. Only in graphite, three bonds are being formed. Only three bonds are being formed, while the other like electron which does not participate in the formation of bond is the electron which causes the movement of electron, or which causes the movement of electricity when electricity is applied. So if a lead made of a graphite, or let's say a wire made of graphite, tends to conduct electricity. That's why we used graphite as the electrode in our electrochemistry in the electrolysis, because graphite itself is a good conductor of electricity due to the valence electron present in the structure of the graphite. Now, while studying about the benzene ring, now how this ring is like structurized. Now each of this carbon, like each of the alternate carbon, like each of the carbon forms a bond with the alternate carbon, like a pi bond. Already they have formed a bond. They formed a double bond. Like how the double bond is like happening. So let's say this is the starting carbon. So this carbon is forming a bond with, let's say I start with a starting arrow. Let's say this is the carbon I'm starting with. So you don't need to give a start. Don't write this, like don't give a like arrow mark whenever you are drawing. I'm just like uh, giving the mark so that like we can trace the starting point. Now this carbon is forming a bond with like a second bond with this other carbon. After forming this bond, as I mentioned, each of the carbon will be forming bond with the alternate, or there will be this double bond to the alternate carbon. So there is this double bond. That means here there will not be any double bond. Rather, to the other carbon, like starting from this carbon to the other carbon to the next carbon, there is going to be this double bond. Similarly, on the next carbon there won't be any double bond. Rather, to the other, like one carbon bond later, there will be this next double bond. So this carbon, like this double bond is actually with this carbon and that carbon. Now how about the hydrogen? Now if we count, we'll be observing that each of the carbon is actually having three of the bonds being like formed. We're left with one of the other, like one bond is being like left over. That bond is basically with the hydrogen. So these are the hydrogen forming bond with each of the carbon. See, now we have six carbon, 1, 2, 3, 4, 5, 6, and we have six hydrogen, 1, 2, 3, 4, 5, 6. Now, is this what it is? No. The other thing is the shape, or this structure, it actually doesn't exist. So this is the wrong structure. Then why did I mention and why did I draw it here? Because I just say this is not the correct, but there is a part where this exists. Like if we, for a slight millisecond, if we tend to like, we can halt the situation, we will be like sort of observing that this is the situation. But in the next moment, if we just capture the picture of the exact next moment, we will see that this carbon is actually like the double bond position has been changed. How? The double position from this portion or this part is changed to the next part. So this is the like, now for every, or like it has been changed, it has been shifted to the next carbons where there were previously no hydrogen, no double bond, but the hydrogen bonds remain same. Okay, so carbon hydrogen bonds remain same. Now is this then perfect? No, this is also wrong. Then what's this correct structure? Why am I not saying the correct structure? I'm just mentioning these are the situation happening. So they are constantly revolving. These bonds are constantly revolving, like they're rotating. These bonds are constantly rotating. So drawing or sketching any of the situation here is not the perfect one, because if I am going to, let's say, draw this or sketch this structure, then this doesn't define the benzene in like the complete sense, because this is just the 50% of the situation. Whatever the other 50% will be represented by this situation. So either of them gives the situation which is of the 50% of the time. That means I'm saying which is having a 50% probability, which is partially true. So because I'm not saying the complete truth. So the complete truth is going to be just drawing these revolving like circle inside that represents that the double bond is actually constantly revolving. It's not in a fixed position. So it is not the same as the double bond we find in the alkene. So don't get confused. This is not the same as having a double bond in the alkene. Why? Because the alkene has had the double bond in a fixed position. Between two fixed carbon, the alkene's double bond was present. But in benzene, the double bond is not present in fixed carbon because this is changing. Initially over here, then over here, then it will come over here, then it will come over here. Like, it will be like constantly changing. That means the position of the double bond is never constant. So whenever we will be having, let's say, this structure, obviously the hydrogens are unchanged, like the hydrogen is not constantly evolving, just the bonds are evolving. So this is one of the way we can draw, or the other way is just this one. So either this one or this one. Without showing hydrogen is also perfect. With showing hydrogen is also perfect. Now, how these bonds are defined? If we want to like, let's say, if you sort of want to visualize or understand how these bonds are like different from normal single bond, like over here, how these bonds are different, how this single bond is different from the other alkane single bond, and how these double bonds are partial double bond. These are not actually double bonds, because if these were double bonds, then it wouldn't have been like revolving. Since they change their position, so they are not actually like the usual double bond. So that's why we are trying to visualize how these bonds are like different. So let's say these are the bonds, and here we have the bond length, like the the height or the length of this bond, like this distance, the distance between these bonds. So how they like differ. So bond length in, let's say, nanometer, because these are like very tiny particles which we cannot see in our bare eyes. So in terms of like the bond of carbon-carbon single bond, which we usually see in like which we normally see in, let's say, alkane or other sort, like other hydrocarbons. So that has a bond length of 0.154 nanometer. Now for alkene, alkene it is 0.134, which is much more like lesser. That makes sense. Like if I'm holding on to something, let's say something is falling from the cliff, let's say I'm on top of a mountain, or top of a cliff, and something is was going to fall down, and I tend to hold it with one of my hand. Obviously I will have less strength and it will tend to like move further. But when I grab the same compound with my second hand as well, like I'm now pulling it with my both the hand, I'm getting more strength, more pulling power. As a result, the distance between this object and like myself, it will be like reduced, isn't it? Same thing is happening. It is pulling it with two hands, so having more attraction. That's why the length is lesser now. But the carbon to carbon bond length in benzene, how does this like looks like? It has a bond length of 0.139. Now see, if this was the same as the alkene, then they would have been the same, similar. But since they are not the same, see the benzene's double bond is actually a bit greater. Or the benzene's carbon-carbon bond lengths are actually a bit uh like, how do I say, a bit taller, or a bit more, a bit greater, yeah, a bit like greater compared to like this one, the normal alkene or normal carbon-carbon double bond, while it is far more lesser than this carbon-carbon single bond. Why? Because there is obviously a presence of like partial double bond. We can say that as a partial double bond, because obviously there is not a singular bond. There is more than one bond is present. Since the second bond is already always like revolving, it is not a fixed. It is not having a like fixed position. That's why no fixed length is there. But there is more than one bond. We can just say that. Now, why this benzene has no reaction with bromine? Because we know the alkene, they tend to have reaction with bromine. Why? Because when let's say bromine is present there, bromine water which has a brown solution, when bromine is like made to like appear in front of this alkene, the bromine, it breaks this bond, the pi bond as well as itself, and forms like bond with this carbon, hence reducing or decolorizing the bromine water solution. So bromine water solution initially was brown, it decolorizes to colorless solution. The reaction happens, but in place, like since there was this double bond, it breaks and forms an addition nucleophilic addition reaction. But sorry, electrophilic addition reaction. But in place of benzene, why didn't have like there any reaction happen? Why couldn't have we any reaction? Because benzene actually doesn't have an actual double bond. So that's not like, as I was mentioning there, like it is not actually the actual double bond. Like it is not the same double bond as the alkene's double bond. It is a different double bond. It's sort of like we can say a double bond. At the same time, we can't say it as a double bond. Why? Double bond means it needs to have a fixed position. It needs to have a constant, like fixed place, fixed position, fixed bonded components in between them. But the benzene over here, or the carbon double bonds over here, is not having fixed carbons, because initially this carbon and this carbon were having these bonds, then they were not the same components which were involved in the like bond. Rather, the other carbon was involved in the formation of the second bond. That's why this is not actually the double bond. So we can say in answer to this question that why no reaction happens with bromine, because no double bond in benzene, so no reaction with bromine solution. Now, if we observe the reaction, or if we observe the structure in place of hybridization we studied in detail in our AS topics. So hybridization. Now, how this happens? In place of this benzene, we get sp2 hybridization. Hybridization. If you have the notes from, or if you have studied it previously, so it's better, because it will be like it will be easier to understand the hybridization topic. So I would urge you to like go through the books and having a slide of, or if you have other sort of note materials, to go through the resources so that you get the gist of the hybridization part, so that like it helps you, because hybridization sort of is a technical topic. So just defining it in like two sentences won't be like enough for right now. So right now, bear with me, and I guess it will be good to go. So sp2 hybridization is where, let's say, obviously we know the electron, like the shells are in a structure of spdf, in that sort of structure. So carbon usually have 1s2, 2s2, 2p2. So the first subshell, the S subshell, has two electron field. It's completely filled. Then the next layer subshell, S subshell, it's also completely filled. Then P subshell, it's P orbitals. It is also completely filled. Like it is just partially filled, because P can accumulate a maximum of 6 electrons, but only 2 were filled. Now we can perform a hybridization here. So carbon, when it's excited state, when it is hybridized, or when it is going to be hybridized, it transfers itself to a, let's say, uh, excited state. What happens in this excited state? It happens that 1s2, and this in together, like this together, this the subshell S and the P, they tend to form a sort of, let's say, a mixture of, like the electrons, they gets like shared among the all the orbitals. So in this, sorry, in this p subshell, there is x orbital, y orbital, and z orbital, isn't it? So for that x part, this, like while there is like only 2 electrons in p, that means each of the electron is in just like singularly in x and y. They're not actually sorry, they're not actually like having a combined effect. Like they're not, like, let's say, like they're not in the x, like both forming the pair. Rather, each of the electrons are in different orbitals. But z orbital is like completely like empty. So what we're going to do, we are going to get hybridized. Hybridization is going to take place. The electron is going to jump from this s subshell to the p subshells z orbital forming 2s1, 2p1, 2px1 actually, sorry, 2px2, sorry, 2py1, 2pz1. So each of the orbitals are going to have now all the like electrons. Each one of them will be having one electron. Now these two, sorry, these three will be participating in the hybridization reaction. So this is like, how can we then define this? This is from S. One electron is from S now. One electron is from P. Another electron is also from P. So we can say sp2. That's how the naming convention for the hybridization comes. So this is the sp2 orbital. So orbitals are now from sp2. So sp2 orbitals. So these are the actually hybridized orbitals, and this z will be remaining as it is. Now we will be seeing just in a moment where this z will be like, going, but so far that's the situation. Now let's say this is the carbon. Let me try to draw it in a three-dimensional structure so that like it helps us to understand what are like the consequences and what are the situation being happening inside. Now this is the singular bonds which have been formed so far, and each of the carbon, let's say, having a hydrogen bond to its part. So let's not draw those because it will be clumsy. It will be a bit clumsy if I try to draw the other bonds, like the bonds which will be like the partial double bonds. So how this partial double bond happens? We have seen previously. Like, you will be observing if you revise or if you tend to read the resources for hybridization that the pore like when hybridization. My tongue is twisting like, frequently. When hybridization happens, the electrons or the orbitals which has been left over that tends to participate in pi bonds. Before forming pi bonds, what happens? They form these electron clouds. They have this electron, their own electron clouds. They have this their own electron clouds. So these electron clouds are for whom? For the z orbital. Now for the z orbital, this electron cloud can form bond with this orbital. So they tend to bend and form this orbital. Over here, they have formed the pair. So there is the presence of the z orbital from this carbon as well as the z orbital from that carbon. So to erase this, so this is now the situation of this orbital. And this is now the shape of this orbital actually. So there is this common like this happens in this way. Let's say these are the two carbons. One of the orbital is in this way now, and the orbital is this way. So in this bit like over here, this common bit that is actually the part of the like where the new bond has been formed. So the bond like the pair has been formed there. So this can happen over here, and the other way happens on the like other two carbons and the remaining two carbons. This can happen for the opposite way as well. How? That means the other direction, let's say instead of these two, now this can be for these two. Similarly, these two and these two carbons. Now one thing, obviously they're changing constantly, but at a time they can have either form like bonds in the upper level. At the same time, we like if we take picture from other instances, we can see rather than having this, they are also having a structure where these double bonds are actually below. So they are actually they can also form the bonds like towards the bottomward, like towards the downward. They can also form this bond like in this way, in this manner, or in this manner. But at a time, they can be on any level, any one level. So either they can be above this, like above the ceiling, like it's at the top, or at times they could be at the bottom. So that means either over there or over there. At a time, they can be over like any one of the like situation, not both at the same time. Okay. So this is the ring of electrons. This ring of electron which rotates due to this like rotating of electron, a ring of electron is formed. That ring of electron is known as the Benzine's pi electron ring. So this is actually not a double bond. Now on we will be actually mentioning that this is the ring, benzene ring. Benzene ring. So this is known as the benzene ring. We get a new term or how to identify this uh, how to identify this actually bond. This is the benzene ring. Now one will be finding this is actually a ring, not no more a double bond. So benzene, as you can see, like it can either be at the top or the bottom, at the or at the bottom. Like the ring could be formed either at the top or at the bottom. Because think it in this way: if you have a circular, let's say, disc, it cannot be like can it be happening like partial of it is at the top and partial is at the bottom? Like, can the full circle be completed in that sense? When we're getting a like a single object, you can get, let's say, a piece over here, another piece over here. Like, you will be having like two separate pieces, but in order to have a singular piece, they have to be on the same plane. That means benzene is planar. Why? What does planar means? Planar means, let's consider the top of your table. The top of your table. In the top of the table, if we like place, or yeah, let's consider it in this way. And one side if you place a pen or eraser or certain object there, and on the other side you also place certain object. Now, aren't these two objects on the same plane, on the same level? For example, the second floor of a building. Let's say the second floor of a building. Let's say there are two units there, so two apartments are there. So aren't on the same level? That's what planar means. Planar means they are on the same level. They're on the same level. So benzene, these carbons are on the same level. These rings, like this hybridized Z orbitals, they're on the same level, and the bond they're going to form, they're also on the same level. That means benzene is planar. And in benzene, each of the carbon is sp2 hybridized. Each of the carbon, all the carbons are, we know, sp2 hybridized, and two sigma bonds are with adjacent carbon atoms, isn't it? Because let's see, this is one of the sigma bond, and this is another sigma bond. So each carbon is forming two sigma bonds to the like nearby to the next two carbon atoms, and one of the sigma bond is with whom? Hydrogen. We cannot forget hydrogen as well. So there are like three in total sigma bonds. Two is with two adjacent carbon, another with the hydrogen, and the remaining carbon, which is the Z orbital, it gives a maximum like orbit maximum overlapping. But how? The three sigma bond we got, each of the carbon having this three sigma bond will be in such a way that the overlapping of these orbitals, this electron cloud, the overlapping of this cloud will be the maximum, so that the unhybridized, that p unhybridized orbital, pz orbital, will be also will have to also be planar, isn't it? Because if they are not planar, if they are like one is at the bottom and another is at the top, then they won't be planar anymore. Because think it this way: if one of the object is here and one of the object is at the below the table, then they are no longer in the same level. If one of the apartment is over here at the floor and another apartment is below the floor, they are not in the same level, no more remaining their planar. So that's what are the characteristics of benzene is actually. Now, talking about the type of reaction they can perform. So benzene initially can perform, like we got to know that benzene has the type of reaction of what? They undergo electrophilic substitution reaction. Obviously, we could understand that a substitution reaction, like the validity of substitution reaction is true in this case. Why? Because they tend to have like, obviously it's a benzene ring, not a double bond, but they might show certain reactivity which resemble this double bond reaction. Like, since there is a double bond, we should be getting what? Additional reaction, isn't it? But since there is no double bond, actually no addition reaction happens. That's why the characteristic reaction of benzene was what? Electrophilic substitution. That is, this, like, even though you can say there is, let's say, the partial bond, double bond, one of the bond gets broken, then we can easily form the reaction. No, that's not going to happen, because if that's going to like gets deteriorated, this bond, then there will be no more this benzene ring. So the component will have no more characteristic of a benzene molecule. So it won't be anymore a benzene. That's why we have to, even if let's say one of the bond is broken, we have to regain the structure. We have to reform this benzene ring in order to have the characteristic of benzene. So this benzene, when reacts with chlorine, let's say for example, it undergoes some sort of substitution reaction. which is known as, in this case, alkylation, or mm, alkylation is basically okay. Before alkylation, let's just go with the like overflow, how this substitution reaction happens. When this chlorine reacts in presence of, let's say, the like we have to obviously provide catalyst and anhydrous FeCl3. It forms this component where we have the presence of this benzene ring. This like, my rings won't be like consistent. They might get smaller, might get bigger, but they represent the same ring. The ring didn't change, okay, but my shape changed because my like it's difficult to draw over here because I don't have a like practice of drawing. Now, how this formation of because electrophilic substitution, that means some electrophile is to be formed. Now let's come to the formation of electrophile. How these electrophiles are being formed. So our this reaction mechanism, step one is going to be formation of the electrophile. So Cl and Cl, they will be having heterolytic bond fusion. So this pair of electrons, it is going to get completely broken, and one of the substance, like one of the atom is going to take the take the pair of electron, and other will be remained with less number of electrons. This reacts with the catalyst being provided, FeCl3. So FeCl3 does what? Takes the nucleophile, and keeps the electrophile. So keeps the electrophile how it is, but takes the nucleophile with itself. So now the nucleophile is in the FeCl3 and electrophile is left over. Now we have the electrophile. This electrophile will get attacked with this benzene ring. So Cl plus, this benzene ring, or we can say also this is a pi electron ring. The name could also be interchanged. We can say benzene ring or pi ring. So this pi ring actually attacks this chlorine, forming a structure of hydrogen and chlorine. Now see, this pi bond gets broken and the positive charge comes in the middle. That means this pi bond is now broken. So, but how is this going to happen? This, after this attack has been done, this is actually step 2. This attack to the electrophile by the pi ring has been done. We have to reform the ring. So reforming the ring is the next step, which is step 3, reformation of the ring, where from this initial position, hydrogen and chlorine, this hydrogen is going to get, like the bond is going to get broken. After the bond is broken, like breaking, this electron, the pair, like the electron over here, this is going to actually like fill in the blanks, like fill in the depths, or let's say it is going to fill the missing portion of the bond of the ring, pi ring, the hydrogen bond, forming the ring and leaving the chlorine here. See, the hydrogen in this case is getting substituted. So hydrogen is being substituted due to the presence of what? An electrophile, which is this Cl plus. So hydrogen was substituted with an electrophile, leaving H plus out of the system. Now the final thing is step 4. Remember I mentioned we must have a catalyst in this reaction. This was the catalyst. So catalyst changed in this situation. FeCl4 minus was formed. Now in order, like what does catalyst mean? It must participate in the reaction. The other thing is its initial and the final condition must remain constant, like it shouldn't be changed. So that means we need to regain or regenerate the catalyst. So FeCl minus Cl4 minus plus H plus, it causes the chlorine to form bond with HCl. So hydrogen chloride is formed plus FeCl3. See, our catalyst is regenerated. So we are left with our catalyst. Same things could have happened with bromine. Let's say if bromine was there, Br2. Same could have happened with iodine, I2. Okay. Now comes the part where we have the named reaction. This is known as a very famous reaction, which is known as Friedel-Crafts alkylation. Friedel-Crafts alkylation. So initially I was like mentioning this one because like I still remember this day, like the because this was one of the reaction which was like very famous and popular because I used to read them a lot. So Friedel-Crafts alkylation reaction. So this is the same thing as the reaction we just studied. So this is the benzene ring, and we will be reacting with an halogen alkene. So a halogen alkene is there. So this condition will be anhydrous, but in this case, this is now AlCl3 instead of AlCl3, AlCl3, and we will be left with this product where CH3, the alkyl is there. That's why it's known as alkylation. So the benzene has been like the alkyl group is added to the benzene. So that means our electrophile will be who? The alkyl group. Now the same react like same process happens. At for the initial stage is what? To form the electrophile, so CH3 and Cl. So if we do it in the other direction, there is this, let's say, the CH3 and there's the Cl. So over here, if it reacts in the same manner, Cl3, the hydrolytic bond fusion happens, negative partial positive, and AlCl4 minus left with CH3 plus. Thus, the other thing happens the similar way the pi ring is going to attack this CH3 plus, forming our like everything is just as like before. This is hydrogen, this is CH3. There is no positive charge here, it's a negative charge not here. Yeah, so then this is going to form the further bond. Like, it is going to further fill the bond, fill the ring with its electron, the hydrogen, and we'll be left with this alkyl alkyl group added with the benzene, and will be H like left with H plus. This H plus in turn will react with this AlCl4 minus to form HCl plus AlCl3. So that's one of the way. Now, if we go further into a depth, we can see that, or let's say, if there are other reactions, if like, let's say if there were like alkyls of greater or much more larger components, let's say we have CH3, CH2, Cl. In that moment, also we can like we'll be doing the same thing, just completely the same thing. The alkyl will, let's say the like field of alkylation happened with in place of what we used here. We used here CH3Cl. Since in place of this we had the CH3, CH2. We get to have further more greater amount of thing. If this was been present, same thing would have happened. Just the chlorine is going to like break the bond, and similarly, this will be our electrophile. There is this step three is going to happen. Step four is going to sorry. So step two is going to happen. Step three is going to happen. Step four going to happen. Finally, we will be left with our H plus, and H plus will regenerate our catalyst. The same things are going to get repeated. So don't get confused. But when let's say alkyl of this was the bigger one, uh, we have let's say components of the same Friedel-Crafts alkylation I'm describing. This is also Friedel-Crafts alkylation, but different compounds could have been like reagents could be there. Alkylation. So let's say instead of now the halogen alkanes we have CH3 POCl. So this is a acyl chloride actually, acyl chloride. So this acyl chloride, how is it going to react? Just give me a minute. So when this acyl chloride is present, the conditions are same. When Friedel is there, this Friedel term, the catalysts are going to be LCO3, LCO3 anhydrous LCO3. So when this is there, the reaction is something like this. So now in this case, there will be this hydrolytic bond fusion. This is negative, partial negative. This is partial positive. We'll be having our this one as our electrophile, and a LCl4 minus will be there. Even if let's say instead of COCl or this CH3 group, let's say this was something very big, let's say C2H5 or other bigger components. So if like there are like other bigger components, it would have been the same thing. Just this CO group would have been here instead. Now what happens? Simply this carbon, it is going to get attacked. This electrophile is going to get attacked by this pyrene. This pyrene, it is going to attack this, like, sorry, not this one, actually, this carbon actually, or the electrophile itself, this carbon. Okay, the positive charge in on whom, the atom which will be the electrophile, it will going to get like the pi ring is going to attack that atom. So after attack has been made, the situation will be something like this: the partial pi ring H, and we have carbon, oxygen, and CH3. I'm just writing in, like, rearranging the structure, and then the next step we will be seeing, observing this hydrogen. It compensates. This was the term I was like looking for, and I was like tongue twisting a lot. The hydrogen is going to compensate for the missing pyrene. So it's going to compensate by itself by losing, by uh, donating its bond and regenerating the pyrene, forming this structure. The benzene pyrene will be regenerated, and C double bond O and CH3 will be generated here. We'll be left with what? Hydrogen. So this hydrogen is going to, or sorry, H plus is going to get reacted to AlCl4 minus, forming HCl plus AlCl3. So we'll be left with this compound. Okay, so that's actually our part for Fidelcraft, like alkylation. One more thing, like, this is a very short part. I think I should cover it up because we should be left it for the next lecture. So further electrophilic substitution can happen. Okay, so for further electrophilic substitution, this can also happen where, let's say, initially we have, like, after alkylation, like after substitution, this is the component being formed. Now let's say we have we have provided, let's say, chlorine here. We have provided chlorine here. This is the situation. Okay, so this is an anhydrous situation. Let's say anhydrous. So now how is going to happen? Already we have one of the electrophilic, like, substitution has taken place. How it is going to happen? Now, if, like, for example, if there's this presence of this methyl group already there, or this group already being there, okay. So if there is this alkyl group, okay, due to this presence of this alkyl group, if only and only if this alkyl groups could be anything. For example, this could also be an alkyl group. Alkyl group could also be like this, CH2. Also can, like, we can have a, let's say, this aldehyde, or let's say a ketone group here. This could also be alkyl group. The only thing alkyl group means is, with this carbon, is there is another carbon bonded, that is representing as a alkyl group. Okay, if this carbon, one of the carbon is bonded with another carbon, that's enough for defining it as alkyl group. Alkyl group means there could be, like, other atoms as well, but the generals are the methyl, ethyl, like this sort of, they are the general terms. But this can also be, like, identified as the alkyl group. So if there's this alkyl group, like either of these or that, but if, let's say, this was there, let's say there's this nitrogen here. Okay, this is not an alkyl group. Why? This carbon is not bonded with a carbon here, so this is not an alkyl group. That's why I'm mentioning, if an alkyl group is there, then due to the presence of this alkyl group, this will be considered as the first group. Okay, this is, let's say, the first position. This is the first position. This is the first position, CH3, and this is the first position. This, if this reaction needs to be taking place, then the chlorine is going to appear in any of this position. Let's say these are the carbons, so let me mark the carbon number. This is starting position 1, this is 2, this is 3, this is 4, this is 5, this is 6. So if these are the carbon numbers, then the additional or the further electrophilic substitution can take place in these groups 2, 4, and 6. These are the position where the further substitution can take place. So let's say if we have CH3 here, okay. Now for the next chlorine, it will come here or here. Sorry. Yeah. But if let's say from here we get, or from here we get, let's say this one CH3, Cl and Cl. The only thing left is the sixth position. So after adding the further chlorine, this one is going to, this sixth position carbon is also going to get electrophilic subsidized. So subsidized and substituted with this chlorine. Then so this is the maximum like number of like saturation. This is the saturation point after which no more electrophilic substitution can take place. So that was actually the portion up until this. I guess this is perfect for till now. Take a like revise the terms, and we will be covering the next parts on the next lectures. Thank you.